here. All right, so like schmuck, I loaded them all into one place. All right, and the other thing, H3, and then the other thing I need is the tables we got to go to. They don't say. Schmucks. Frank, do me a favor. Back of the book, W shapes. What page is that on? 486. Cool. All right, so we're going to do a little flip-flopping back and forth here, unfortunately. We are recording. We're here. Okay. So if you look at this one, go large. Structural steel wide flange is reinforced with two pieces of steel attached to the web of the member as shown. Calculate the moment of inertia of the built-up member with respect to the XY or XX centroidal axis, so the center of the beam. This happens. This happens quite a bit out in the real world, all right? Because somebody just can't get the right shape they want, but they can make it up. Okay. So when this happens, this isn't as easy as just going out to the W18 by 71 and pulling off the section modules. Okay. The cool part is, half the problem we already got known data for. The other two pieces, the pieces of steel we put on the outside, we got to calculate. Okay? So we're going to look for that I, those two pieces of steel, and then sum them together to get the whole. Fair enough? And just so you know where we're heading, is when we do the bending, we got to deal with MC over I. Know where that is. So we got to always know where the centroid is, and we always got to know where the moment of inertia is. Not where it is, but what it is. Okay? So literally that's what we're up to. So hopefully come Monday, I'm thinking Monday, depends how the day goes, we'll get into some bending help. Okay? You can start seeing the fun that goes with those. Okay? But we got to get this stuff kind of mastered first. All right, so long and short of this, W1871, okay? So here's where we're going to get C6. So I apologize up front. W18 by 71. Right across here, okay? And so as long as you are here, it's a good idea to write down all the parts and pieces, okay? And I'm going to write them down so I can transfer them over to the other page here. So we got an area, and that is 20.9. Henry, you're going to need, there should be 2 pages there, I think. There's probably 4. All right, we are going to need the I X value, which is 1170 inches to the 4th, okay? And just for sake of fun here, go all the way over to the S value, which is 60.3. Okay. Okay. And just so that you guys are following along here, God, that's confusing. Our area, our moment of inertia, and then 60.3 is the S value. Oh, really? Oh, it is for the Y, 15.8. Thank you. Okay. And if we needed to know the Y, it's all there. But all the other stuff's there. So let's go back here and have a little view of what's going on here. So we got a D. That's our overall dimension, right? We need D. No, we don't need D in this case. Okay. But if we were actually taking those apart piece by piece, we would. But here's the thing I don't want you doing is, yes, you can treat this as a rectangle, that is a rectangle, and that top is a rectangle, except for the fact that we got these curves in here, okay? And that you're going to miss. Are you going to miss it by a lot? It won't be that big a deal. But trust me, that is in there because that adds strength to the material. Okay? So we do really want to account for that. But if you had to do you don't have the manual with you and you have no idea what it is, 3 rectangles, do it, find the centroid, everybody's hunky-dory, and you're close enough for gumbo. Okay? And then just slap a factor of safety on it to be safe. But trust me, if you're going to sit down and do a real design, you're not doing back of an envelope calculation. Okay? You are sitting someplace with all the references you need. Guarantee it. Okay? If you're not, go someplace where all that's there. Don't crash a polar lander into Mars for no apparent reason. Okay? So all we actually need is the area and the, actually all we need is the I, but I wanted to show you this table. The TW, that's the thickness of the web. That's important sometimes. And TF, the thickness of the flange, is up here. And the BF is the width of the flange itself. Okay? So get used to this table. You're going to see it and use it quite a bit. Might as well have it handy when you're ready to go for it and know where it is. All right, so we have a, whoa, what am I writing with today? We got an I of the W18 by 71 that is actually equal to 1170 inches to the fourth, okay? Nothing complicated there. We don't even have to get into a lot of the other stuff, do we? Okay, we're not looking for the areas and all that stuff. Just simple, find the shapes bit. I tried to make a couple of these easy up front so you didn't have to struggle with these, but I want to show you some of these pieces. All right, the I for the plates is going to be what? So we got a plate that looks like this. 15 inches by 1 inch. Okay? So we got a base times the height cubed over 12. And I'm going to multiply it times 2 because there happens to be 2 of those we're going to play with. Fair enough? All right. So if we go plug some numbers in here, what are we going to get? I'll give you the 12. What's the base? 1. Thank you. And the height cubed is going to be 15. All right, so 15 cubed divided by 12 times 2 give us a grand number. $562.5. And then watch your units and make sure it's inches to the fourth. Everybody good? Okay, so do I really need to carry the 0.5 out there? No. So round it up to 563. In this case, it's a good idea to round it up because we're going to make that larger. Okay. All right. So then I total will be the I of the W plus the I of the plate. So 1170 inches to the fourth plus the 563 inches to the fourth. One other little safety thing here to keep your eye on with this, not safety, but if I did 2 up here, I'm good in the plate, multiplied that. But if I only did that for 1 plate, make sure down here you add 2 plates, okay? Don't care where you do it, as long as you bookkeepingly keep it straight, okay? Otherwise, you're going to have a problem. What's that turn out to? 1733, okay? Now, that was just to calculate the I. If I want to know the C on this, we need to go back to our table, and we're going to look for that D on the 11 by 17, which is something I should have wrote down while I was there, is 18.5, right? Okay, so back here, the D value here was 18.5 inches. So C is D divided by 2, and 18.5 inches divided by 2 is
9.25.
9.25. Okay. So literally now we know everything. If we had to go figure out the stress, we know that, and that we'd have to do some calculations ahead of time for. Okay. But that's where we're heading with that. Okay. If you take a look at this for a moment, what do we do to this thing? So if we just had the 1170, right, we stiffened it up by putting the extra plates on the side of it and gave us a greater moment of inertia. Okay, so it can carry more of a deflection or bending or twisting load or any of that stuff. Okay, that's why we do it, and it happens quite a bit. I'm not a structural engineer, but I would venture to say that 80% of the time you can just pull a standard stock size, okay, and the world will work. The other 15% of the time, you're making something weird, okay, which is why they pay engineers. Anybody go to the job fair yesterday? You see today's steel?
Yep.
So they make some really interesting connections with buildings. Okay? Guaranteed, everything they make is top. Okay, but where they can get away with standard steel in the main pieces, they do. But on all their connection points, they're reinforcing things and adding all kinds of stuff. So It's got a little bit more metal to it. And if you saw one of the coolest ones they've ever done, you know who Patty Hearst is and who her father was? So Patty Hearst was this crazy woman that basically hung out with a bunch of criminals in the 60s. But her father ran the Hearst newspaper syndicate. And the Hearst building down in New York City is this egg-shaped spiral that came out of the original old brown sandstone building. And all that steel was made over here in Gouverneur. So it's a cool company to work for. I'm not trying to advertise for them, and just some interesting facts about it. Okay, everybody good on that problem? So that would be the answer we'd need to actually go through to do the moment bit we're going to do next week. Good? All right. Now let's have a little bit more fun. Let's go down and take a look at what I give you. 8.9 is a... Is that the right one? Yeah, 2 inches. Okay. And then I gave you, did I put these backwards? Oh yeah, I gave you the Z. Well, let's do the one from last. Yeah, we'll do this one. All right, quick cut and paste. And I gotta go to here. Go away. Back over to here. Paste. No. You can come off for the time being. All right, so we are going to be doing this one. Now this one's a bit more in tune with what we were doing. Okay, and this one is problem 8.9, and this is letter C. So if you're following along in the book. All right, so how do we start this one? Actually, what are we looking for first? It is calculate the moment of inertia with respect to both the centroidal axis for the area shown. Okay? So what do we want to do? How are we going to do this? Yes, we're going to find them both. So this is that point in time where it's time to either decide to make a table or just run a bunch of equations. Okay? And I want to do the table first because it will make the whole process make sense to you, I'm hoping. Okay? It has in the years I've taught it. Okay? So let's label this one part 1. We'll label this one part 2. Okay? And just to keep them straightened out in our mind, I'm going to put a circle around them. All right, so we got 1. We got 2. All right, we need y bar, we need a, and we need a y bar. And then we can find I want to do this in a table. Well, I guess I'm going to do it this way. X bar, A of X bar, and then we got I of X and I of Y. All right. I think I got them all in there. All right, so we got to establish a 0, don't we? Where do you want to call the 0 on this plane? Oh, you know what we need? What did I miss from the table? AD, didn't I? AY, AD. Tell you what, let's skip that part. I'll just do that on the table, or calculations. We'll do this one. So Y bar for part 1 is 10 inches, right? So what's the centroid of this 10 inches? Five. Okay. Part 2, the centroid for that is?
7.
Just the part itself, not the other bit.
1.
1. Okay. The areas for these are? Ten times 2 is 20. And what's the other one? 28. I should put the units up here too. Inches squared, inches, inches cubed. I'm going to save this part over here for the, we'll just do it separately so we can just keep our head in the same direction here. Okay. All right, so we are 5 inches there. We are 1 inch there. Okay. All right. 5 times 20 is? 1 times 28 should be 28. So far, so good? Okay. All right, X bar. So now looking at it the other way, you may have an answer.
For the Y bar, do we know
Not yet. That's that part where I go A times D in the moment of inertia equation. I'm going to do that separate. Okay. Right now I'm just trying to find the centroid and the areas of each individual shape.
So if it's asking this for the one over in the do we need all this information? Wouldn't we just use the dot equation for this?
No, because you have 2 shapes. Or 2.
But we had 2 shapes in the last one too, and all we did was the dot.
Yeah, but we did it because it was a rectangle, and we just slapped it into here. Go. I see what you're saying. Yes, you could just take the 2 and add them together.
Yeah.
But what you don't get is where the centroid is. That's part of the problem. You got to know where the centroid is. On the first shape, the centroid was across that x-axis. Okay, where 0. Which is why I went out and took 18.5 and divided it in half, got 9.25. Clear? Everybody else clear on that one? Anybody not clear on that one? Because that's a really good question. Because yes, ideally, it's T-shaped. We have 2 areas, we're good, but we don't know where the centroid is. We do need to know where the centroid is. Yes?
Is there a reason we didn't want it down stuff?
The reason it's 5 and not 6.
That's what Montana.
Yes, that's what he was just asking, or Montana was asking. When we go down to find the moment of inertia, we're going to have to go base times height 2 divided by 12 plus area times d. Okay? And then d is going to be the distance. Now we figure out where our baseline is and go up. But the y for the part is the centroid of the shape we're playing with, not the overall piece. Good? Diane, you good with that? Okay? It's not a topic that's easy to get your head around the first time. I guarantee it. Okay? So nodding your head, just to nod your head at me doesn't help me. Okay? It won't help you either, but you're good, okay? All right. Now, in the X, let's pick a different color for X. Let's use blue. Now the X is going to be about this one. So where is this located in relationship to all this? Okay. So the centroid for this one is actually 7 over on 2, right? So 7 inches. Okay. And our other one is still 7 inches, right? Or is it? So I brought it from this edge over to here to 7 inches. That's for 2. What's the centroid for 1?
0.5. No.
Just 1,
One.
right? And where was I going with that? I was trying to get you caught in that paying attention to the outside edges. Yes? You clear, Carter? Okay. Ah! Yeah. Okay, so you were just nodding your head at me a few minutes ago when I explained Carter's answer. And you got this at the centroid of object 1 of this complex shape is only 1 inch over from the right. Okay, so that's 1. All right, the area is still the same. We didn't change the areas. And if you did, God help us. That's a squishy object that will not stay in place. If you can create a beam out of that, let me know. All right, so 1 times 20 is 20. 7 times 28 is 196. Okay? So far, so good? The area is the same, but this is area times x bar. So this is inches cubed. All right. Now, and for the sake of doing this, I think I'm going to add the I bars, or the I's in here. I about XX, and the I about YY. Okay, just so we got them, put them in the table. But the real truth of this is I of 1 in the XX is base times the height cubed, bless you, over 12 plus the area, what was that? Area d squared, right? From yesterday. Okay, so we're going to play with that. So the base on 1 is 2 inches, correct?
So it's cubed.
It's base times height cubed divided by 12. AD squared. All right, so we got 2 inches for that. We got 10 inches cubed divided by 12 plus the area for 1 was 20 inches squared. Now the D for this is going to be what? So, and I actually should label this D of 1. So if I got to pick a baseline here someplace, right? Now is the point of choosing your base. Or you could have chosen in the beginning, you just kept it in the back of your mind. But right now is the point where I got to know a base. Okay? Where's the logical base for this? At the bottom. I like the bottom. Things that sit flat on the table are always a good spot. But you could pick the top. Okay? But I wouldn't try to pick something in the middle. It just gets really complicated. All right. So I'm going to call this x0. Okay. So, actually, sorry, that's y0. So I'm going to go up to here, and this is D1 in the value I'm looking for is 7. Everybody good with that choice? You see why I'm doing it? Dustin? Okay. Frank? Yeah? Yeah, or?
No, I'm not.
Okay, let me explain. All right, so I gotta go from, actually, where am I moving? That'd be really handy. Black.
Oh, yeah, I did.
People get hurt that way. It's only funny if you, only folks in IO. That's the old story. All right, so we know from this line here up, 5 was the centroid of that part. I established this distance out here as my base that I'm going to take all my measurements for the second half of this equation from. Okay? So that D is really all about from here to that center. Okay? It would be good. Now, I missed a step, didn't I? Why didn't you tell me, Carter? I was having too much fun trying to get to this. I missed a step, didn't I? I did. What did I miss? So I need to know where y bar 0 is, and that's the summation of ay bar over the summation of the area. I'm glad you were confused, Frank. All right, so 20 and 28 is 48 here, 128 there. Okay, take this back to black. So 128 inches cubed over 48 inches, and that gives me a value of what? What do you got, Henry? 2.66. Inches. Okay, so right about there is my YO. Okay, so this was all in error. So I got to go from there to there is my D1. Okay, so this turns out to be 2.66 inches. So what is the D value I'm looking for? 5 minus 2.66 equals. Is that where you were lost, Frank? Yeah. Please don't. Thank you. Boy, I was getting too excited and having too much fun. And trust me, if I can do it, you guys can do it. Have fun. Yeah, no. Can you get lost in your calculations? Yes. So the trick to this is practice and remembering the steps you're doing. What do you guys got?
2.34.
2.34?
34.
So this goes down into here as 2.34. All right, now what do we get for this value? $226.18. Okay, everybody good?
I got 276.18.
I got
276. Oh, sorry. Someday when we get back to the point where we don't have masks on, we'll all be able to hear each other. It's almost somebody needs to invent a mask that goes, the microphone built in that goes to your phone that projects out. Isn't that neat? Who wants to make $1 million?
Could be malaria for your phones if you make
I'll take anything to help right now. Actually, maybe hearing aids would help on my end. You know. So we got it there. Now, what's the I2 for this? So it's the same equation. And the only thing that should be in discussion really is the D value. We are 6, 6, 12, 14. And 2 inches divided by 12 plus the area of that was 14. We do that area right up here? 28, yeah. What's that? Can't hear you, Andrew.
Oh, square instead of the 2 inches.
Oh, thank you. Get out of there. Now you're going to be a pain. Okay. So what's the D going to be? So we're going from here now. So that'll be D of 2. So we're 2.66 to the centroid of part 2. Is 1 up, right? So it's 1 down. So 2.66 minus 1. 1.66. 1.66. Anybody disagree? Nate.
So 2.66 is fine from y equals 0, right?
Where y is equal to 0, it's where this thing will balance itself out on my finger.
So 1 for D1, should it be 7 minus 2.6?
Now,
So
yeah, it's because I put that y is equal to 0 in there, and I was going down that merry little path that we put in earlier. Okay, so the process is this: find your areas, find the centroid of each part, calculate the area times the centroid to get your AY bar, and then sum those together and sum the areas together to find your true centroid of the part. Okay, and that's where everything's pivoting about. Okay, so that y0 there just doesn't need to be there anymore. It was there because I was trying to get a baseline to measure from, but I'm not measuring there. So I'm really looking at this point right here. So if I did this with if I was to put this thing in motion, it would pivot around that point. Okay, that's where it's going to twist. So that's the point of balance that we're looking for. So everything's got to go around that point of balance. That is the new 0 where everything. Okay. Nate, you good?
Why are we subtracting 1 from this but not?
So we are going from 5 to this at 2.66. We're going to get that moved to that point there. What the AB1 was. That 2.34 inches. And then from here to there, you're gonna get that distance. Good there? Everybody else good? This is good timing to have this on a day where it's got 2 hours. All right. So we did 1.66 right down here. And the answer for that turns out to be 86.49 inches to the fourth. So I of x is I of 1 plus I of 2, and that's equal to 276.18 plus 86.49 inches to the fourth. And that is what number? 369.67?
62.
62.
No, 362.67.
Okay, so that's that one. Okay. We do the same thing for the y's. Anybody care? We'll try another problem here.
I just had a quick question. So for the equation that we use for I and X, I had that written down for the equation for I and Y. Did I write that down wrong?
I may have said it wrong yesterday.
So I had it down as I and Y, Y is H.
Yeah.
So that's I X X then.
Depends on the book. XX is always moving this way across the page, and YY is always moving this way across the page. To me, it's YY, but we'll go with whoever else is both this question. So XX, the X plane goes up and down the Y. X is equal to 1, it's always up and down. Y is equal to 1's up. We'll do some research, get back to it.
Okay.
I'm always pretty sure it's 1 Y.
Like Y for that equation, or?
Yeah, it should be YY, because it's, where are we going up on the Y-axis? So in order to be on the map coordinate system, we went up Y 2.66.
So then with how you think it is, so this would technically all be like I is Y.
That is YY. Yeah, the D for those would all be on the same. Pretty kind of good? Alright, let's try it again. Let's try a different one. All right, let's go do some cutting and pasting. here. We'll take that one. Okay, so here's the next fun one. Okay, now this one's kind of cool because this actually is going to be, where's the centroid of this actually going to be? Right there, okay? So that's kind of saves us a nice bit of sanity here, doesn't it? No guessing, you know, top, bottom. It's really those T-shapes or things that are off size, and just have to deal with them. All right, so let's do well, I'm just trying to think, is there really a reason to do yeah, that's what I'm trying to think of. I think we can skip the table for this one. Everybody kind of good? See why? Because literally this side's the same as that side, and then we got the centerpiece here. So we really wind up with, you know, if I was to do this separately, we could do pieces like that. I could do pieces like this, whichever way you want to go. I'm just looking at the author's solution to see which way he did do it. And I believe he did 1 inch. Yeah. I'm going to go with the way I first drew it. We'll divide it there. So this is 5 inches overall there, and 5 inches overall there. That makes sense? As long as we do it the same, or not the same, but consistently, we're good. If you choose the other way, you should get the same answer. Okay. All right, so let's do, so area of 1, and I guess that's going to be this, will be 1, and then we'll make this one, sorry, 2, and we'll make this one 3, but then we're going to have area of 2 equals area of 3. But the area that's going to be 5 times 1. Whoops, that's area 1. Is 8 times 1. And this one will be 5 inches times 1 inch. Okay? Everybody okay with that? All right. So the next bit of this is the I for 2. Now let's do I for 1. We'll just keep it in the right numeric order here. I1 is base times the height cubed over 12. Our base is 1 inch. Our height is 8 inches, and that's cubed divided by 12, and that gives us a what value? .67 inches to the 4th. So far, so good? Okay. I2, whoops. I2 is the base times the height cubed over 12. Its base is 5 inches. Its height is 1 inch. And 5/12 is 0.42. No, really. Oh, crap. There's something we do have to do here. Son of a pup. Okay. Yeah, we can do this one tableized, but what just happened to these things? We got to have this area and the d squared on it. Why? Yeah, they got to line it back up. It's that bit where I just threw my arms out and spun in circles. You know, I got that extra mass out there, and it's got to get back to the center, not just the centroid of the one part. Okay. Sorry, that's why I was questioning that, Tyler. All right, so if we do this one, it's 5 inches, 1 inches cubed over 12. The area of that is 5 inches squared. And we got to go from the centroid to the centroid of the part. So what's that going to be? .5 inches. And then we get a number. That's going to make a difference in it. .6. Everybody agree? Okay, so I total will be I1 plus I2 plus I3, and we don't have to do 3 again unless you really want to, but 42.67 inches to the fourth plus 101.6 inches to the fourth plus 101.6 inches to the fourth. Or you could write it as 42.67 inches to the fourth plus 2 times 101.6 inches to the fourth. And get you the same answers. And if you do this right, you get a grand number that looks like 246 or something like that.
45.8.
245.8. And that's your moment of inertia. And your C is, depends on where you want to draw your baseline, but it's going to be at x axis right now, which would be 4, 5, 5 inches from the bottom if you really wanted to know where it was. Okay, you got to measure from someplace. 4 or 5 inches from the top. We are going to know the C. Somebody starting to get the hang of what moment of inertia is about. You had a question there?
Yeah. So why did you use a different formula for the I2 and I1?
Because I1, everything spins about its centroid. Okay. The centroid for objects 2 and 3 is way off center, and they all got to go back to the center point. Okay. Which is going to get where I was heading here. So that's a good lead. Thank you. I don't know if you planned that or even if you got this far, but I need you to use your imagination for a little bit. I'm sure none of you have experienced this. When they were getting astronauts ready for space, you understand gravitational effects they were going to be put under when they thrusted them off the surface of the planet on a Saturn V rocket at all kinds of tremendous power. They literally put them in a centrifuge. Okay? And it spun them until they were sick. I'm sure a lot of them did. I don't think it was way not good. But they had to get them used to it. And the trick is this: if I have an object and I can spin it tightly around the center of the it doesn't have very much momentum. Okay? Therefore, it has very little gravitational effect on things. Okay? But the further I move it out, 20 feet from the center, if I spin it really fast, it's going to have a huge gravitational effect, or the gravitational effect that they always talk about with fighter pilots, pull 4 Gs. They pull 20 Gs, they pass out the cockpit. But it's always that effect of what the gravitational pull is on things, okay? If you think about this particular shape, this L, okay, and it was actually out in space, it was a space station, okay? Out on the flanges at 2 and 3, you would have normal gravitational effect. So you'd be able to stand up and walk around there, okay? But the closer you get to the origin or the C point at 5 inches off the outside edges into the center, you would have no gravity. Because everything out here is spinning with momentum, but in the center is not, okay? And it's the same effect that goes on with wind turbine blades. So the hub, they don't really rotate really fast with the hub, velocity-wise. It's the tips that are going out to 150 miles an hour, okay? Because of the length. Right? They got to get that sweep caught up with just a little bit of motion on the hub. Now, granted, the hub's not that big. The hub's like 3 feet, 4 feet diameter. But that tip way out there, 200 feet out, is trying to catch up with a little bit of space in here. There's really no stuff going on in here. It's all out there. Same with this. If we look at this, if we were going to bend this beam, where is it going to rotate about? It's going to rotate about the center axis at XX. But as it starts to twist or rotate in space, we're going to give it some momentum, okay? And that is why we call it moment of inertia, because it's the inertia of that object rotating out in space, okay? Now, it's kind of corny. We're not really out in space, but the laws of Newton still apply, and they haven't changed any. Okay? You can always think of this stuff out in space. So somewhere in your world, you got, I think I asked this to you guys, you learned about moment compass, right? Or did I explain that the other day? I explained it the other day. So you got a center axis here, and we got a force over here. Okay? We got a distance between the force and the center. Well, that's the same thing that's going on here with the centroid. There's the centroid, but now I got all this mass out here, and it's going to want to move. And my job is to keep it from moving. So I always put a moment couple on it to keep it in place. Okay? Make sense? All right. Cool. You guys need a break, or you want to keep trucking along? Need a break. Okay, let's take a 5-minute break and come on back in. We'll do one more of these. See where we go. See which ones I want to do. Because you know, whichever ones I don't do, you're going to get for homework. Justin, pick one of those in there that you'd like to do next. looks like a magnet. Actually, it's some wooden timbers, but yeah, we can do that one. Cool. That?
That one looked easy, so I want to keep that one. So I'll go with the last one. Go into the last one. Go do the last one. Do the last one.
Do the last one.
Yeah, 8.5, right?
Yeah. Wait, no.
Not
That's the
too
last one. Oh. Yeah, I only think it's 8.7.
This is similar to first one out there.
Okay, all right. 8.12. The people have spoken.
812, okay.
They have spoken.
All right. That's fair.
Fair enough.
Either 8.12 or 8.30.
Well, you two are going to have to Indian wrestle in the middle of the floor here for it. You know. $8.12 is not bad. What was the other one? 8:30 is not horrible. I'll give you a hint on 8:30 though. If you do this, does that make it a little different? You got two triangles there. You could do a trapezoid, like so. Just a matter of finding the shapes you want to play with. Okay, so we are doing this one. Everybody back? Yep. How about we do this one with establishing the base down here, and we'll actually use the y is equal to 0. I think that should help you, Nate, try to see the difference between things. Take the base down there to the bottom of the flanges. Just to show you the different way of going about it. Alright. Do you want a table for this, or do you not want a table for this? Okay. Alright, so let's do, we want to call these things first. So, we'll call this one 1. And this one 2. And then this one is 3, but really it's the same as 2. No, 3. Okay. And they are the same things. They're C15, 40. Okay. All right. Let's do this. Oh, we need the table. So 1, 2, 3. Our Y bar, our area, and the area Y bar. Okay. So let's do the areas first. The first one's easy. 27 times 1 is 27. Okay. The area for the other two, so go out and get the C15 by 40, and you're going to have to go to the appendix there, but I'll give it to you, is the area for that is 11.8 inches. Okay. Now, I want to go get some measurements off that table, so I'm going to go there. AC. So this will be, what I'm looking for is the D for that. So C, 1540. D is actually 15 inches. Cool, one that actually is on the nose. All right, the Y bar for that is, where'd it go? Well, it'd be 7.5, but it's not listed there. Cool. All right. So back to here for a bit. All right. So this distance there to here is 15 inches on the nose. Okay. So the Y bar for 2 and 3 is 7.5 inches. Okay. Given the fact that we're going to go from the bottom. All right. So what's the Y bar for the plate up above?
0.5.
Say it again.
0.5.
No, not in this case. 15.5. All right, and the area I got already was 11.8 for both of those. Okay, so AY is for each of those. What you got? Anybody? 418.5. So we're going to tally that one up. So the summation of this one is okay. AY summation is 795.
Five.
795.
95.
Oh, 90. 595.
Yes, 0.5.
All right. So our y naught is going to be located at the summation of a y over summation of a, 595.5 inches cubed divided by 50.6 inches squared, and we get a number that looks like what? $11.8. Everybody good with that? Which means someplace in here, we're probably right there, is 11.8 inches up from here. Okay. Far so good? Okay. Now for the fun. Well, should always be fun. Just how can they mow the lawn today? All right, so I of 1 is base times the height cubed over 12 plus a1, and now we got a d squared in there. So what's that d going to be? (27 inches times 1 inches cubed over 12, right? And the area for that was 27. Yeah, 27 inches squared. And the D from that centroid right there, so D1's got to go down to that point there. What's that going to be?
So it's C point five, so so what would be 15.5 subtract from 11.2?
15.5 subtract from 11.3.7. Yes.
3.2.
3 point what?
2.
No, I got this.
I got 3.73, but I carried extra a few places. $15.5 minus 11.8.
3.2. Oh no, 3.7.
3.7. Tell you what, I'll even write this out so we can't have any. D1 is 15 plus 0.5 for the centroid plus, or I'm sorry, minus the 11.8 inches, right? That's the height of the C channel. Whoops. That's the centroid of the plate. And that's the Y naught that we found earlier. Okay. So 3.7 inches and square that. And what do you get for I1?
371.9.
371.9. Everybody agree? Carter shaking his head no.
Well, like it has, I got it, I didn't do it.
There are so many places in here make mistakes. No.
I really, I appreciate it.
All right. 3.71. Okay, cool. We have agreement. All right, how about I2 and I3? Now, I'm going to ask a really dumb question here in a second. Just because, why am I adding this in here? Why do I want that in there again? Louder.
It's area of 2.
No, it's not the area 2.
To revert back to the
I gotta take it back to why not, or real centroid of this combination piece.
It's what?
Take it back to the centroid. So, I know this is 15. So its centroid for the C channel is right here at 7.5 inches. Okay, so that's that centroid. But because I have all this extra mass out here, its real centroid of this combination of three is at 11.7. Okay. So D2 and D3 are equal to 11.8 inches minus 7.5 inches, and that should come out to be 4.3. Make sense? You good, Alosh? Okay. All right, so we go down here. We are cool. Oh, well, could have saved yourself a lot of hassle here, couldn't we? Did I write down what the IX or the I value was of the C shapes? Idiot. Anytime you go to those tables, write down everything on that table that could be important, because you're going to go back to it over and over again. Just like this. So, I for a 15 by 40 is 348. Okay? So far, so good there? All right. So if I was smart, I would have written that down back someplace in the beginning of the problem. So I really don't have to do this. 348 inches to the fourth. And a little note here. Go to table in appendix.
Would we have, like, what would we put down for a base of that? Like, would we have gone just for the bases, if it's not shaped?
For the C channel itself,
Yeah.
it would have been a base across the bottom.
Oh, I didn't know.
You can't. Now you're back to trying to guess what that curve is inside the channel.
Yeah, because we wouldn't have been able just to do the I.
Right.
Would we?
No, And that's why I was, so when you get back here, folks, and you start looking at this thing, and you got this channel in front of your screen, or on your book there, that's not a flat piece and then a curve. It's actually a curve with a taper to it, and then we got a curve out at the end. So that's actually made by squeezing it through a set of rollers, all right? And they keep the back flat, and they keep this flat, actually they're perpendicular to each other just because of the way we use different material or different applications. But the inside of this is all kind of got some curves to it. That's pretty uniformly thickness across there, but there's no way you could actually do that. You could, if you really tried, calculate, get your Y someplace off the table here, and figure out what that is. It's a standard curve to it. Somebody knows exactly, but most engineers don't. And we just go to the table and take it out. Okay. So, in the beginning of this problem, I should have come down here and wrote down area. It'd been nice to get the height, so I knew that that was 15 inches. I'm not so worried about the BF flange thickness there, but that's kind of useful to know because that's that dimension across there if you really need to know. But that's much of our problem. The average TF of the flange, that's the thickness across here. You know, it's the average. Could you do it? Yeah, you could use that. But why bother? And then the X bar and the IX, and you're good to go. Okay. I just write those down. Just save yourself from flipping back there. Or the other little note I have, I'll tell you, if you got the paper back, you got the book, stick a sheet of paper in there so you can flip back to it really quick, or go buy some of those little sticky tabs and stick on those pages so you can flip those open when you need them. Because you're going to go from the problem to the appendix to the problem, and then back from the problem to the appendix. Okay? It's just worth writing it all down. Just take it down as given stuff. All right, so now where are we at here? All right, so we got to get our area. So the area of 2, please tell me I wrote that down someplace. Yeah, 11.8, right? Now what's the D going to be? We just did that, and that was 4.3. And our number is, and if you're going to make a mistake in this part of the problem, 2 places. One is getting the wrong D, and the other is forgetting to square the D.
11.8, that's what we squared.
Yes, thank you. Yep, otherwise we'd have some really weird combination of units. What do you got, Frank?
586.9.
5.8.
6.9.
6.9.
I've got 566.18.
That's what I was thinking, 560 something, not. $568 point what?
566.18.
566.
Yeah, I got.
Okay. All right, and I3 will be the same thing. So we go do all this. The IT will be I1 plus 2 times I2. Okay. And 372, let's say, inches to the fourth. 566 inches to the fourth times 2. And 15,000 something. 15,004. Cool. All right. And we already know our Centroid because we got that up there, right? Cool. Everybody kind of good? Think you can handle the rest of these for homework? And let's say we make it do. I was gonna say make it do Monday, but that's insane. But then if they make it do Wednesday, then they're screwed up again. We're not back on our Monday schedule. Let's make them do Wednesday. If you got questions on Monday, I'll be glad to answer that. I don't know if this Monday morning schedule thing's ever gonna work again. All right, if anybody's got questions, don't hesitate to ask. And please don't be bashful. Other than that, you all have a good weekend.